Okay, here's the recording in progress. So, okay, so we're over here. Whoops. Set up a little bit here. All right, so 9.2 is on direction fields and Euler's method. I did one direction field last time, and I'll do a couple more today. They could get fairly long. Of course, it's shortened because I've already pre-made these, but when you do it, it's not really hard. It's just tedious, long. So you're going to make a table for me, 49 entries, 7 by 7, 7 this way, 7 this way, from -3 to 3, -3, -2, -1, 0, 1, 2, 3, both for X and Y. And here we go. Okay, so your format is to always set it up like this. Again, if you want to put a sample like this on your cheat sheet, you're allowed to. Just go ahead and put something like this. So X across the top from -3 to 3, Y on the left column, 3 to -3. Again, it should be this way because that's the way it is on the XY plane, right? Negative Y is down and positive Y is up. And we end up with a graph like this. These are slopes. Okay, so the differential equation looks like Y prime equals a function of X and Y. This side only has Y prime, doesn't have Y double prime, doesn't have Y prime plus 3 or Y prime plus Y, just plain old Y prime. This side can have X and Y. Okay, so every point in the XY plane will have a particular slope, right? So you just draw a little tiny stub for that slope out of my field of 49 here, 7 this way, 7 this way. Okay, so yesterday I did number 9, and today I'll show you 10 and 12, and that's all we were going to do today. So we may end fairly early again today. The other topic for this section is Euler's method. Again, that really should be a separate section in my opinion. So I didn't feel like starting a brand new section today for that. And I'm okay if we say that for tomorrow. If I look according to schedule, we were okay to do that tomorrow. Well, I would still actually even be a day early. Okay, so we're going to be okay with that. Okay, so 9, yesterday was pretty easy because the differential equation Y prime equals a half Y, it only involved Y, didn't involve X. So if I go left and right for X, it doesn't change. So once I calculate one of them, right, like 1, then it's just 1, 1, 1, 1, 1, half, 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 and so on. But now if you have a differential equation like number 10, Y prime equals X minus Y plus 1, now it depends on X and Y, and you can see it's a little bit harder to fill the table, right? Okay. So Y prime equals X minus Y plus 1. So what do? You always start off with this. Okay, so if I give you something like this on a quiz or homework or test, always fill out like so. X here, Y here, -3, -2, -1, 0, 1, 2, 3, 3, 2, 1, 0, -1, and so on. Okay. This is natural. I mean, I don't think anybody is going to put 3, 2, 1, 0, -1, -2, -3. This you have to be a little bit careful because you may be used to putting -3 on top, -2, -1, 0, 1, 2, 3. I'll just go ahead and say in all the years that I've been teaching, nobody's ever messed this up, but sometimes students will mess this up because you might think, oh, I'll do the negative and the positive. No, it's the positive on top and the negative on the bottom because that's the way it is when I graph points in the XY plane, right? Positive Y is up, negative Y is down. So you're going to have these 49 numbers, 7 by 7, right? Keep in mind we're, quote unquote, we're only doing 49. There's infinitely many points, right? I mean, there's points in between all around here, right? And there's points way out here and up here, right? We're only doing 49. But, there's a point there, and there's a point there, and there's a point there, and there's a point here, and there's a point there, and there's a point, a million miles that way, and so on. We're just doing the quote unquote nice ones. All right, so I take this differential equation, Y prime equals X minus Y plus 1. You basically just plug in. You plug in the X and the Y, and the result put over here, which will represent a slope. Okay. You're only doing 49, which is a lot smaller than infinity, but it's still 49. Okay, now what happens a lot for these, it's really arithmetic or elementary algebra at the worst. You're plugging in. Okay, if you can see some nice patterns, go for patterns. Okay, so one thing I noticed right away, x minus y plus 1. I noticed one thing would be nice if x and y are equal. Okay, so I look for nice patterns. If x and y are equal, what do you know about x minus y? 0. Plus 1 is 1. Okay, so that means along the main diagonal, I'm going to have all ones. Okay, so notice 1, 1, 1, 1, 1. This is -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, 3. Right? Because if I put in x and y that are equal, they just cancel out, and you would just have 1. Okay, so I can fill this diagonal fairly easy. And say, well, okay, whatever the nice things I can do. Well, another nice thing to do is to let either x be 0 or y be 0. Okay, how about let's say y is 0.
I couldn't quite hear you. Could you please repeat what you said?
So if we have y is equal to 0, y equals 0,
0 is an integer.
then I just have x equals 1. For some reason, noise here, but okay. So y equals 0, then y prime is x plus 1. Okay, so here's y 0. I'm just going to go x plus 1. So add 1 to x, -2, -1, 0, 1, 2, 3, 4. Right? Likewise, how about I try x is 0? It's usually easier to plug in x is 0. And then I have -y plus 1. Well, it's a little bit clumsy, but it's workable. Opposite of y, add 1. Okay, so opposite of -3, add 1, -2. Opposite of 2 is -2, add 1, -1. Opposite of 1 is -1, add 1 is 0. Opposite of 0 is 0, add 1 is 1. Opposite of -1 is +1, add 1, 2. Opposite of -2 is +2, add 1 is 3. Opposite of -3 is +3, add 1 is 4. Okay, so again, you can just faithfully fill in all 49, one by one. But if you see nice patterns, go for it. Like here, right? I just said, oh, a nice pattern is if x and y are equal. That's like 0, 0, 1, 1, 2, 2, 3, 3. Then when I subtract a 0, so I'm just going to have 1. So 1, 1, 1, 1, all the way down here. And sometimes it's nice to pick the extreme points. So the upper left, upper right, lower left, lower right, and then you can get a pattern maybe. Okay, well, we already did this one. 1, 1. We already did this one. How about way down here? Here, x is 3, y is -3. So 3 minus a -3, 6, plus 1 is 7. How about up here? X minus y, -3 minus 3 is -6, plus 1 is -5. Okay, even if you didn't see this, you could start filling. I know it's kind of hard because I've already filled it all out, but you can kind of follow the pattern. You will notice as I go along either left, right, or up and down, the numbers seem to be off by 1. In which case you can just fill the table. Like if I got -5 and 1 here, for differential equations like this, it's quite often, oh, I'll just go -4, -3, -2, -1, 0. Likewise, if I go down, right, you just say, oh, 0, 1, 2, 3, 4, 5, 6. That's true throughout. Okay? So that kind of helps you fill the boxes, so to speak. Now here it was too easy because my differential equation did not even involve x, so I didn't even worry about it. Okay. But here, a nice pattern is, it seems like adjacent squares going either left, right, or up or down are off by 1. You're either going to add 1 or subtract 1, right? So if you notice a nice pattern, add 1, add 1, add 1, add 1. Go this way, add 1, add 1, add 1. And you can just fill that out. So, oh, I got the pattern. And then you just fill the rest of it out. And there we go. Okay, so that takes care of the table. Okay, so you'll be able to fill out the table, hopefully. Yes, there's 49 entries, but normally if you can find a pattern, it would make things much, much nicer. Okay. All right, now take these 49 numbers, 7 by 7. Imagine you copy and paste right here. Okay. After all, this is the origin, right in the middle, 0, 0. Way up here is 3, 3. Down here is -3, -3. This is what? -3, 3. This is 3, -3. Take these 49 numbers, plunk them right down here. So imagine on the XY plane, you've got -5, -4, -3, -2, -1, 0, 1. -4, -3, -2, -1, 0, 1, 2. Okay. Right on the x-axis, it would be what? -2, -1, 0, 1, 2, 3, 4, all the way down to the bottom row, 1, 2, 3, 4, 5, 6, 7. Imagine those 49 numbers that are here, right? You say, well, how come you didn't write those 49 numbers? Okay, I don't actually write the numbers. I draw a slope at those points. Okay? Because we're saying y prime slope is equal to what if you have on the right-hand side? The right-hand side generally has x and y. And yesterday's problem was a little bit too easy. There wasn't any x and y, it was just y. Here, x and y. So I just draw a tiny little stub at that given point. Okay. And the ones that are the easiest are slopes of 0, 1, and -1. Okay. Slope of 0, you know from algebra 1, it just means horizontal stub. So that occurs up at a diagonal, it looks like. So -3, -2. Here's -3, -2, right? 1, 2, 3. And if I go up a diagonal, slope is 0. So notice horizontal, 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 horizontal. Okay. These 1, 2, 3, 4, 5, 6 correspond to slope 0, 0, 0, 0, 0, 0. Then slope of 1 and -1. Slope of 1, you're going up at a 45-degree angle. You know that from algebra 1. Slope of -1, you're falling at a 45-degree angle. Okay, so I notice along the main diagonal, -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, 3. Slope is 1. So right here, 45-degree angle, 45, 45, 45. Okay, and I notice this will lead to one solution, right? It looks like I just follow along the straight line, which is a solution. We don't call it an equilibrium solution. Equilibrium solutions are horizontal, but it does lie on a line. Okay, so in this slope field, if you were to drop a particle anywhere on the line, it would just follow along a straight line path. Okay, then I notice slopes of -1 here, 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 and here. So again, notice the slopes are the same when I go up a diagonal, 45-degree angle. So -3, -1. Let's see, -1, 2, 3, -1. Slope is -1. So falling at a 45-degree angle here, 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 and here. So here, 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 and here. Notice these are falling at a 45-degree angle. After that, well, you just make them steeper. Okay. So 2, 2, 2, 2, 2, 2. So below a slope of 1, slope of 2. Okay, how do I do it? You just kind of, you're basically faking it to a certain extent, but you're eyeballing it and say, okay, if I follow the pattern, I would go over 1 and up 2. Well, you could just pick a point here that's going to land me right on the grid. So over 1, up 2. So I'm aiming from here to here. That's a slope of 2. So just draw me a little stub like that. And then since I know that parallel lines have the same slope, everywhere along this diagonal, I just copied the slope of this one. So that's a slope of 2, 2, 2, 2. Okay. You can just kind of eyeball it. I'm not going to dock you for not getting it exact. I didn't get it exact either. I just drew one of them and then just kind of copied the rest. Slope of 3 is steeper. So slope of 3, let's see, that's the point, what? 3, comma 1. So 1, 2, 3, 1. I made a slope of 3. So eyeballing, I just get over 1, up 3. I just kind of aim it like that. And same for that one, and that one, and that one, and that one. And after a while, these get so steep, I just try to make them a little bit steeper. So slope of 4, which is 3, 0, steeper. And 5 is a little steeper. And 6 is a little steeper. And then 7 is the steepest of all. I make this very close to vertical. Right? That's over 1 and up 7. That shoots way up. Okay. So you can see I'm just making it steeper. And then I do the same thing with all the negative ones. Right? So -2. Let me pick a point. This is where -3, comma 0. Okay, -1, 2, 3, comma 0. Slope is -2. That's over 1, down 2. So I aim from here to here. And in algebra 1, you would have drawn the entire line, but now we're just drawing a tiny little stub. And everywhere along here, it's also -2, -2, -2. And then just make it steeper, -3, over 1, down 1, 2, 3, -3, -3, steeper, -4, -4, and finally steepest, -5. All right, so these 49 little stubs, stub, S-T-U-B-S, okay, make my slope field. Mind you, this is a very small sample of the whole thing. The whole XY plane is filled, right? There's more way out here and way out here and in between, but we're just doing the nice ones. All right, they ask you to draw 3 solution curves, 3 fundamentally different ones. Okay, so the fundamentally different ones would be, well, along the line and something above and below the line. Okay, so if I go above the line, the way the lines are going, I would kind of, looks like it's curving like so, and then going asymptotically toward y equals x. And then if I'm below the line, it looks like they're all curving that way, right? So curving like so. So here are 3 fundamentally different solution curves. So it says give 3 solution curves. You shouldn't just pick them all like on this side, right? With the 3 different types. Okay, along a straight line and then maybe one above and one below the line. All right, so that was number 10. All right. Okay, 12 is a little bit harder. Y prime equals xy minus x squared. And they say to draw only one solution curve that passes through 0, 1. So the wording of that. Okay, so number 9 and number 10, sketch 3 solution curves. 12, sketch the direction field, then sketch a solution curve that passes through the given point. So you only have to draw one solution curve. Okay, so xy minus x squared at the point 0, 1. So notice my final answer, there's only one curve because it just said, just drop the particle at 0, 1. All right, so for this one, I felt it was easier to factor first, x times y minus x. All right, so same thing. You're always going to draw this basic shape, x like that, y like that, -3 to 3 for x, 3 to -3 for y. Again, it has to be this way because that's the way it is on the xy plane. 3 is on the top, -3 is on the bottom, right? Okay, again, to me, the slow ways is just go one by one, that. But it's a lot faster if you look for patterns. Okay, I see another pattern similar to the last one. What happens if x and y are equal? X and y are equal. This thing's 0. Okay, so again, along the main diagonal, I would just have all zeros. What is this machine want to do now? Okay, so 0, 0, 0, 0, 0, right? There's -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. X and y are equal. So 0 all the way down here. Okay. And the other thing I also notice is what happens when x is 0. When x is 0, the whole thing's automatically 0. So x is 0, 0, 0, 0, 0, 0, all the way down here too. That's very nice. Okay, and what are the nice patterns? Well, I don't know. How about x is 1? If x is 1, it's going to be that times that. That means I can pretty much ignore that. x, right? So just go y minus x, or y minus 1, okay? So 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0, 0 minus 1 is -1, -1 minus 1 is -2, -2 minus 1 is -3, -3 minus 1 is -4, and so on. Okay, so that's nice. How about if x is -1? If x is -1, then I want the opposite of this, right? Which is basically x minus y. -1 minus y. -1 minus 3, -4. -1 minus 2, -3. -1 minus 1, -2. -1 minus 0, -1. We already had that 0. -1 minus a -2, 1. -1 minus a -3, 2. All right, other patterns that you can try are the extremes again. You already got that, you already got that. This is -3, 3. Put a -3 here and a 3 here. -3 times, let's see, 3 minus a -3 is 6. -3 times 6, -18. And I like to do this one also. 3, -3. 3 here, 3 here, -3 here. -3 minus 3 is -6. Multiplied by 3, -18. All right, the rest, it's kind of hard to come up with any nice pattern. I notice if I go horizontally, I don't see any nice pattern. I do see a nice pattern vertically, if you notice what's happening vertically. After a while, if you go this way, you may notice, hey, they're 3 apart. So I keep adding 3 here. Here it looks like you keep subtracting 3. And that's true. You'll notice that pattern. And can you see what happens here by pattern? So sometimes if you notice that pattern, right, after you do maybe a couple of them, you say, hey, it looks like I keep subtracting 2, or at least like I keep adding 3. Just go ahead and fill in the chart and you're probably right. But you may want to double check yourself by plugging in some numbers from time to time. So yeah, let me just do this one. This is -2, 3. -2 here. 3 minus a -2 is 5. So -2 times 5 is -10. Okay, -2, comma 2. -2, comma 2 minus a -2. -2 times 4 is -8. And yeah, after you do enough of these, you say, hey, there's a pattern. It's -10, -8, -6. Okay, just follow that pattern. -4, -2, 0, 2. And yeah, we already did this one. It looks like the pattern is you just keep adding 1. We did this one. It looks like you keep subtracting 1. And yeah, this is kind of a strange pattern. Okay, you could say here you add nothing. Here you subtract 1. Here you subtract 2. Here you subtract 3. So subtract 3, subtract 2, subtract 1, subtract 0. How about add 1, add 2, add 3, which is correct. And yeah, you could make up some kind of pattern going this way, but it's probably not worth it. It's too complicated, in my opinion, to try to figure out what's going on if I try to go horizontally. But vertically, it definitely looks like there's a nice pattern. So yeah, sometimes the pattern only works well in one direction, I suppose is one way to say it. If you try to go the other way, you don't get anything that's nice. But at least this time, at least you get something nice going down. Okay. All right, so again, I'm taking these 49 numbers, plucking them down right here. So right here is supposed to be this. I'll use my 2 pens. This is -18. This is 0. This is -18. This is 0. The origin is 0, and so on. All right, slope of 0, anywhere x is 0, which is the y-axis. Okay, 0, 0, 0, 0, 0, right. And where else do I have a slope of 0? Along the main diagonal, along the line y equals x. So 0, 0, 0, 0, 0, 0, 0. Okay. The next nicest ones are slopes of 1 and -1, because slope of 1 goes like that, rising 45-degree angle. Slope of -1 goes like that. But this time, I guess I don't see that many. Let's see, where's the slope of 1? There's one over here and one over here. And that might be just about it, right? Do I see any more slope of 1? Maybe not. So that looks like, let's see, that is the point 1, 2, right? And that would be the point -1, -2. So there it is, slope of 1. And slope of -1, I don't see that many either. I see one here and one here. And eyeballing it, I don't think I see anything else. So yeah. So slope of -1 is at what? -1, 0. There it is. And 1, 0. There we are. And then most of the rest of the time, just make it steeper or less steep. Looks like this grid has more negatives than positives. Okay, slope of 2. So -1, -3 is right there. So I'm aiming for here, right? Over 1, up 2. I got my stub of a slope is 2, and then I draw another one there. And any more 2s? Yeah, these two way up here, slope of 2. And I think that's all the positives, right? I don't even see any more positives. The rest are negatives. Okay. And yeah, usually you don't have to go in order. I recommend going from smallest to largest in magnitude. So in other words, I'll go with -1, then -2, then -3, and so on. So -2, there's one over here and one over here and some more over here. So let me pick this one, which is 2, 1. Okay, so that's supposed to be a slope of -2. That's over 1, down 2, aim in that direction. And then I look for all the other -2s in the chart, like there, and like there, and like there, and just make them parallel. And they just keep getting steeper and steeper. -3, 3, 2. So that's steeper still. Over 1, down 3. And I try to copy that way over here, and over here, and over here. And then I try to look for -4, right? It's a little bit steeper, and so on. And you just keep going. By the time you get to -18 is practically vertical, right? So I drew it almost vertical. As long as you get the general shape, I'm not going to literally measure and see, is this slope -18 or -17? I really can't tell the difference, right? So the whole idea is just get it steeper. Okay. So if you're in the ballpark, I'll give it to you like that. Okay, so you can see most of these are negatives. That translates over here that, okay, my stubs are mostly going down, not that many going up. And there we go. Okay. Then the initial condition is 0, 1. So if I drop the particle there, it was a horizontal stub. So the way the lines are going, it looks like it will curve back up. And where did it come from? The lines here are going down. So maybe it's parabolic. Is it really a parabola? I don't know, but that's our best approximation that we're going to do for this. Okay. All right, so that's the concept of slope fields. So I literally did all of these problems. And then here we had to do what? 9, 10, 11, 12, 13, 14. So 6 of these, I literally did 3 of them. So I did exactly half of them. And you do the rest that are there. And then the next time I'll get started with Euler's method, which is the rest of the problems, which are 19 and on. So Euler's method for tomorrow. So right now, you should know how to do everything up to 14, I guess. Okay. And Euler's method is 19 and then 21 and 24 all. And that's where we're at. Okay. So tomorrow I'll do the rest of 9.2. So we're here, we're good. I will more than likely get started with chapter 10 before the test, as I said, on Friday, 10:15. Okay. All right, we're finished for the day, folks. So that was that. Let me stop the share and see if there's anybody who has a question in the chat. And if not, then we're finished. Okay, anybody with a question, please?
Just something really quickly. So for those questions that you just did earlier, is that something that we can see in the exam in the future?
That will be kind of questions you'll see in the exam, yeah. So I'll say, draw the slope field for this differential equation. So you make the table. I don't want to switch back, but the table that we just did. And then you'll be making the slope field also. Yes, I realize it might be time consuming, so I'll keep that in mind when I construct the test.
Cool, thanks.
Okay. All right, any other questions, please? Otherwise, we're done. All right, then have a good day, everybody. We'll see you next time. Okay, bye.
Thank you.
Thank you.
Take care.